As we begin multiplying and dividing complex numbers, what you'll be doing is basically foiling or distributive property, whatever works for you. Whether you have to write out FOIL, because I've seen students do that. 3 times 7 is the first term on each of those. 3 times 2i, okay, that's 6i. And then the inside term, or distribute 5i to each piece, gives me 35i. And then 5i times 2i is 10i squared. So a couple of things to remember is that I squared is actually equal to -1. So this entire quantity becomes -10 that I need to combine with that 21 in front. So 21 plus -10 is 11. And then combining the other two terms gives me 41i. So you just have to practice this over and over again. It might take you some practice before you get a good handle on everything, but you get -6 as I distribute. Negative times a negative is still positive, 4i. Inside is 18i, 6 times 3. And then 6 times -2 is -12i squared. But again, I squared is -1, so that turns this into a plus 12. -6 plus 12 is positive 6. And combining these two terms together gives me 22i. And then just one more in this, and again it's just foiling, and so you get -20 minus 12i, and again I might make a mistake, so feel free to call me out on it. Positive times a negative is negative. I times I is I squared, but remember I squared is -1, so that's going to do -3 times -1, which makes it plus 3. When I combine with the -20 in front, it gives me -17, and then 17i, minus 17i. You may remember from a while ago that we talked about multiplying conjugates together, and I kind of gave you a heads up that this is going to be very important when we do complex conjugates. So that's exactly what's happening with these problems. And so if you look at this problem, and you're considering well, first of all, what makes things complex conjugates is that the real part stays the same. If you notice that 4's stay the same, but you negate your imaginary part. So a plus bi and a minus bi. So notice that this is 4 plus 2i and then 4 minus 2i. So when you go to FOIL this, 4 times 4 is 16, what you'll notice is the outside and the inside terms cancel each other out. And then 2i times -2i, as I do my last term, is -4i squared. So what's super important here is the outside and inside terms cancel. I squared is equal to -1. That if you multiply by -4 turns into positive 4. And 16 plus 4 gives me 20. So what I'm trying to get at is you can multiply complex conjugates together and you end up with a real number. Notice that we get rid of the imaginary parts. So let's see if that happens for every. So again, you can confirm that these are complex conjugates because the real part stays the same and you just negate the imaginary part. So -5 times -5 is positive 25. The outside term is positive 5i. The inside term is -5i. And I times, well, positive times a negative is negative. I times I is I squared. And what you'll notice is that's the same thing as minus -1. So 25 minus -1 means 25 plus 1, or 26. And just one more to practice. Again, they're complex conjugates because you get real part with real part is staying the same. The outside is -18i. The inside is positive 18i. So again, those imaginary parts are going to go away. And then the last term becomes negative because a positive times negative is negative. I times I is I squared. But as a reminder that I squared is equal to -1. So you get 36 plus 9, or 45. So the whole theme on it is what exercise 3 is all about. What's true of these products is multiplying complex conjugates together gives you a real number. And you can show that that's always true by, okay, so we have the real part, the complex number a plus bi. So its complex conjugate is a minus bi. And as we go through the process of foiling that, or the distributive property, you get a squared. The outside term is a negative abi. The inside is a positive abi. And then the last term, positive times a positive is, positive times a negative is negative. B squared I squared. And I think you can see, I hope you understand, that those middle pieces cancel. So this is the same thing as negative of b squared times negative 1. Well, negative times a negative is positive. So we do end up with what they say, a squared plus b squared, which is exactly what they said it was going to be. So you can memorize this, but I don't. And if I don't think you should. But that's going to help us get to a method that we use very often in math. And it's a method that you'll just need to know how to do. So what we're doing is we're looking at this piece, 3 plus 2i over 4 minus 5i. And for some reason, I don't actually know quite the reason, is math people don't typically like imaginaries in the denominator. So our goal is to get rid of the imaginary I in the denominator. Okay. I think it's an old school method, but we still ask you to learn it in Algebra 2. So anyway, the thought process is this, is if I consider 4 plus 5i over 4 plus 5i, you have the same thing on top and bottom, that's equal to 1. So the thought process is, if I take this problem up here and multiply it by 1, 3 plus 2i over 4 minus 5i, if I multiply by 1, it's still the same value. It will give me the same value, whatever that value is. And I know it's imaginary, so it's kind of a weird concept. But instead of multiplying by 1, what we're going to do is we're going to multiply by a number that's equal to 1. And the thing that's equal to 1 is what they said right here, 4 plus 5i over 4 plus 5i. And the reason for that is we just learned, and if you didn't notice, 4 plus 5i is the complex conjugate of the denominator. And that's why we do that, is we just learned that multiplying by a complex conjugate gives you a real number. In other words, it gets rid of the I in the denominator. So that's what I'm going to do. I'm going to actually show the work over here, because if you look in the denominator, you get 4 times 4 is 16. The outside term is 20i. The inside term is negative 20i. And negative 5 times positive 5 is negative 25. I times I is I squared. And from there, you could see, okay, those pieces cancel. This becomes 16 plus 25, or 41 in the denominator. But you still have to do all that work in the numerator, because you can't get rid of all the i's. That's why they just choose the I in the denominator. 3 times 4 is 12. Notice I'm foiling. Outside is 15i. Inside is 8i. And the last term, 2i times 5i, is 10i squared. But remember that this is a negative 1. So 10 times negative 1. So 12 plus negative 10 is 2. And 15i plus 8i is 23i. And that's how we get rid of the I in the denominator. So the thought process then is that we could do that for any problem. And what you have to, because I'm done telling you what to multiply top and bottom by, you just have to know that you want to multiply top and bottom by 5 plus 3i, the complex conjugate of the denominator. And as you get good at well, I don't think you need to memorize, but I'll give you a heads up that what I do is I typically start to FOIL the denominator. 5 times 5 is 25. I know in my head the outside and inside terms will cancel, and then I just do the last term, minus 9i squared. But it is okay if you memorize the rules and you're just like, okay, well, 25 plus 9 is 34, so that must be my answer there. But you do need to FOIL the top still. 10, and then 6i, minus 20i, minus 12i squared. Double check my arithmetic, or let me know if you're confused or I get anything. Because remember, the I squared makes that a plus 12. 10 plus 12 is 22. And then 6 minus 20 is negative 14 with an I. So maybe I'll just explain a little bit more. Look at the denominator. What's its conjugate? 4 plus 10i. So you have to multiply the top by the same thing. 4 plus 10i. And that's okay, because what I'm really doing is multiplying this thing by 1, and I'm not changing the value of it. So again, I might just do the denominator first. I know the outside and inside terms will cancel. So that's going to turn into 100 plus 16, or 116. And then do the top. 22 times 4 is 88. And then 220i. And then 12i, and then 30i squared. But as a reminder, this turns into a negative 30, so 88. Well, 80 minus 30 would be 50, so it's got to be 58, plus 232i. Now, kind of a heads up, and I haven't been doing it yet, is if all these numbers are divisible by the same thing, they do want you to reduce. So it might be useful to use a calculator. Like starting with my green one, you could actually divide each piece by 2. So if I follow that answer, let me try to type it in really small, would be equal to, if you divide every piece by 2, it would be 11 minus 7i over 17. For instance, I could tell right off the bat this next one, all of them are divisible by 2, but there might be a bigger number as well. 58, I don't know, is that divisible by 4? No. So that might be your best bet, is dividing everything by 2. And I have to tell you this because you never know with a multiple choice question if they reduce everything. So it would be 29, 116, and 58. And notice that the I is still part of the problem, 116i. There we go. So just so you're heads up, like on a free response question, you might be okay just doing each one of them. Now, if we do the reciprocal, I kind of want to jump ahead. I know I skipped the previous problem, but I can go back to it if I had time. The reciprocal would be 1 over 3 plus 9i. So the thought process is, again, multiply by its conjugate. So you don't want to just jump into an answer. So in case you forgot what a reciprocal is, there's your reminders, 1 over that number. So if you work with the denominator, the outside and inside terms cancel, and then you end up with minus 81i squared. So that's going to be over 90. And as I mentioned before, you can actually divide each piece by 3. And that's what I mean, is each one of these looks a little bit different. But if you divide each piece by 3, you get 1 minus 3i all over 30. And in other pieces, you can actually just split each one up by 30. And 3 over 30 would reduce even further to this correct answer. So I ran out of time. You are ready for the homework. Sorry I didn't get to all of the exercises, but